Welcome back. To grasp the fundamentals of PLC ladder logic, we must first understand how the PLC processes the on-off input signals and how these signals are interpreted by the PLC logic to control the state of the outputs. Imagine that inside each input connection to the PLC or module, there is a tiny imaginary control relay with a normally open and a normally closed set of contacts, because that is exactly how the controller sees them. We've used an actual relay circuit to explain the operation of this imaginary relay. A lamp is connected to the normally open contacts, and the limit switch represents our external input device. When the switch sends a yes or on signal to the relay coil, its normally open contacts close, switching on the light. Now we will rewire the relay circuit, but this time we will connect the lamp through the normally closed contacts. The lamp remains on until the switch is activated and the normally closed contacts open, switching off the light. When we replace the relay with our PLC, we see that the imaginary PLC relay responds in exactly the same way as the real relay. Now, this is what happens inside the virtual world of the PLC when we select a normally open contact in the logic. Initially, when the external device is not sending a signal to the input of the PLC, the output point is off. But as soon as we send an on voltage signal to the input, the output turns on. Exactly the opposite condition occurs when we select a normally closed contact in the logic. Initially, the external device is not sending a signal to the PLC, and the output point is on. But as soon as we send an on voltage signal to the input, the controller switches the output off. We use symbols to communicate these instructions to the logic of the PLC, because the PLC is programmed in exactly the same way as a relay is wired. This symbol means pass power to the output when the input is sending a voltage signal. And this symbol means pass power to the output if the input is not sending a voltage signal. Now let's apply what we have learnt to a simple control circuit. In this example, let's suppose that we want to turn on a motor when the start switch is activated. First, we enter the start switch into the logic as a normally open contact, and we specify the switch as an input device with address location X0. On the same rung, since it is an output device, we enter the motor as a coil with address Y0. When we activate the start switch, an on voltage signal appears at X0, and the imaginary internal contact associated with input X0 closes, and power passes along the rung to the output coil Y0, which turns on the motor. We call this type of circuit an examine-on circuit, because it is telling the controller to examine the input location for an on voltage signal, and if it finds it there, to pass power along the rung. Now let's consider the opposite situation. Suppose we want the motor to be switched on when the input is not sending a voltage signal to the PLC. We enter the start switch into the logic as a normally closed contact using the same address locations as before. The motor now runs as long as the voltage signal to the input is off. But as soon as the start switch is activated, sending an on signal to the PLC, the motor stops running because the imaginary normally closed contacts have opened, breaking the flow of power to the output. On a ladder logic diagram, we refer to these contacts as examine off because the logic is telling the controller to examine the input location for an off voltage signal, and if it finds it there, to pass power along the rung. Now let's apply this logic to a simple series or AND circuit consisting of two switches and a motor. The start switch is wired to input X0, and the limit switch, which we'll call the safety switch, to input X2 on the PLC. To the output location Y0, we'll connect a motor. Using the programming device, we'll enter a set of normally open contacts to examine the start switch X0 for an on condition, and a set of normally closed contacts to examine the limit switch X2 for an off condition. When the external devices send the correct messages to the PLC input circuits, the output Y0 switches on, energizing the motor. We can express this condition by the following statement. If all conditions on the rung are met, then the rung is true. To recap then, the normally open or examine on contacts ask the question in the logic, is the address location X0 receiving an on signal? And the normally closed or examine off contacts ask the question, is the voltage signal at address location X2 off? Only when the answer to both these conditions is yes will the motor turn on. Let's examine the operation of this circuit on our PLC training panel. We'll begin with the start switch sending an off signal and our safety switch sending an on signal. In this instance, neither condition on the rung is being met and the motor remains off. Now we activate the start switch and a voltage signal appears at input X0. The contact X0 on the ladder rung changes to its active state and closes, passing power along the rung to the output. Notice, however, that the power flow has stopped at contact X2. This is because the logic is asking the question, is the safety switch sending a voltage signal to input X2? And the answer is yes, until we deactivate it. Once X2 is deactivated, the logic finds the condition it was looking for. Both conditions are now met, and the rung is true. Power flows to the output Y0, turning on the motor. That's how the PLC combines on and off signals from various input devices and decides whether or not to pass power to output devices. In the next module, we will explain the ladder logic diagram of the block sorting machine, taking each rung step by step. And then we'll look inside the controller to see how it makes decisions and keeps track of the control processes. This completes our discussions for Module 3. Practice these examples and others with your PLC trainer so that you can fully appreciate how a PLC uses the principles of relay logic to make decisions and to manage a system.